Hi, my name is Xiao. In this video, I will introduce our work understanding intrinsic robustness using label uncertainty. Motivated by the empirical hardness of developing robust classifiers against adversarial perturbations, researchers began asking the question, does there even exist a robust classifier? This is formulated as the intrinsic robustness problem, where the goal is to characterize the maximum adversarial robustness limit for a given robust classification problem. Built upon the connection between adversarial robustness and classifier's error region, it has been shown that if we restrict the search to a set of imperfect classifiers, the intrinsic robustness problem can be reduced to the problem of measuring concentration. Many efforts have been made towards understanding the concentration function for different input distributions and perturbation metric. However, if we take a closer look at the concentration problem, it turns out that it has nothing to do with labels. In other words, no matter how we assign the labels to the input, such a notion of intrinsic robustness will remain the same. This is counterintuitive because learning an adversarially robust classifier clearly depends on labels. Therefore, we propose to incorporate the label information for defining a more meaningful notion of intrinsic robustness. As an illustration, if we consider a synthetic 2 Gaussian distribution with L2 perturbations, we can immediately prove that the least expansive region is a half-space that is far from the 2 Gaussian clusters. Correspondingly, the optimum constructed classifier for intrinsic robustness will treat this half-space as its error region. In contrast, if we train a classifier to separate the 2 Gaussian clusters, we can imagine that data points that are around the class boundary should be more likely to be misclassified. This motivates us to introduce label uncertainty as an indicator of the likeliness of a given input to be an error point. We formalize the notion of label uncertainty using the underlying class conditional label distribution and the label assignment given by the ground truth classifier. In our experiments, we make use of the CFAR10H soft human labels as the best approximation we can obtain for the label distribution of CFAR10 images. A high uncertainty score indicates that there is more discrepancy between the original CFAR10 label and the CFAR10H soft human label. We hypothesize that images with higher label uncertainty are more likely to be misclassified as errors for machine learning models as well. We conduct experiments on CFAR10 to test these hypotheses, where we compute the error region label uncertainty and the risk for classifiers trained using different model architecture and learning methods. Error region label uncertainty stands for the average uncertainty level for all the misclassified inputs. This figure reveals a strong correlation between error region label uncertainty and risk. As models become more and more accurate, uncertain inputs also become more likely to be misclassified. This further suggests that in order to make the intrinsic robustness problem more meaningful, we should actually measure concentration for uncertainty regions. Specifically, we impose an additional label uncertainty constraint to the standard concentration problem to focus on subsets with high label uncertainty. Correspondingly, it can be translated into an intrinsic robustness limit with respect to the set of imperfect classifiers whose error region label uncertainty exceeds some threshold gamma. This figure illustrates the intrinsic robustness estimates we obtain by incorporating label uncertainty, shown as the green dots, on CFAR10 with L-infinity perturbations. The orange dots represent the prior limits converted from the standard concentration function, which does not involve labels. The blue dots stand for the performance of the state-of-the-art robust models documented in RobustBench. Our intrinsic robustness estimates being much lower than prior limits suggests that, compared with the concentration of measure phenomenon, the existence of uncertain inputs may explain more fundamentally the adversarial vulnerability of state-of-the-art robustly trained models. Thank you for listening. If you have any questions, please feel free to contact me or stop by at our poster at ICLR 2022.